recursive functions more natural compared to writing iterative ones, right? Because in iterative functions, you have to do a lot of manipulations with respect to variables, and typically you tend to lose track of variables if there are many of them, right? So if there are 2, 3, 4 variables, and you're trying to update them, process them, manipulate them, it's fine. But once the number of variables grows, and you are trying to manipulate them within a loop, then it becomes a slightly more complicated. And then even if you're trying to verify an iterative code, right, it becomes complex, because suppose you have like 5 to 10 variables, and you are trying to understand what those variables actually store and what is happening within each iteration of the loop. What are you trying to do, right? You will have to spend time to be able to come up with loop invariance, right? So we talked about how to prove correctness, how to verify, how to check whether what your program doing is correct. If you have an iterative kind of a function, what you use to prove correctness is something called loop invariance, right? So loop invariance, right? So this is like a property that is correct, okay, or the property that holds, okay, in every iteration of, okay, of a loop, right? So note that coming up with loop invariance might not be that simple, right? So it depends on the context. You have to be clever about it. You have to think about, okay, what is the right loop invariant that I can use to prove the correctness of the program, right? On the other hand, if you have a recursive function, then things tend to become simpler, right? Because the very structure of the recursive program, what are you trying to do, right? So you're trying to solve larger problem, so larger problem in terms of solution of smaller ones, right? So that is the general idea, and that is why you write recursive functions. You're trying to solve a problem of size, say n, okay, and you realize that if you solve problem of size, smaller size, say n minus 1 or say n minus 2, then you can combine the solution of these smaller problems to construct the solution of the problem of size n. That's exactly what happened when you wrote, when you consider the Fibonacci number, right? So Fibonacci, right? And you realize that the Fibonacci of n can indeed be written down as Fibonacci of n minus 1 plus Fibonacci, whatever, n minus 2. And it has this recursive structure. And that's why you can write a recursive program. And that's the easiest program that you can come up with, right? So that is the main idea behind recursive program. Whenever you can write a larger problem, you can solve a larger problem in terms of by combining the solution of smaller ones. Recursive program or recursive function is the most natural one to write. Okay, so let's go back to Towers of Hanoi, because I had a sense that a lot of students might have had a problem understanding that. Okay, so I can do something else, right? So if people over here are comfortable with Towers of Hanoi, then I can move on to something else. So type in the chat window. Do you want to go over Towers of Hanoi again? All right. Okay. Yeah, I understand. Right. So it's a tricky it's a tricky problem the first time you see it, but then you realize that a recursive way of thinking about it is actually the most natural way of approaching this particular problem. Okay. So here's the power. Okay. So the problem is the following. You have three sort of poles. Okay. Okay, and now you have these disks. Okay, so let's name these poles. This is called pole A, this is called pole B, and let's call this pole as C. Okay, now you have these disks. Okay, that sit on these poles. They have like a hole in the middle. Suppose you take an example with just 3 of these disks. Now, the problem is to move these disks one at a time so that the end configuration should look something like this, right? So it should be all the 3 blocks should be on the third disk, right? So that is, you want to go from this configuration to this configuration. But the issue is that at no point during moving these disks, a larger disk can be placed on a smaller disk, right? So that is the issue that you want to that you're trying to solve. Okay. Now, our recursive strategy or recursive way of solving this problem was the following. Okay. Now, suppose we are talking about, in this example, we are talking about 3 disks, but in general, we can talk about n disks, right? So you want to move n disks from pole A to pole C such that at no point during the movement, any larger disk is going to be on top of a smaller one, right? And you have a help disk be able to do that. Now, the recursive approach for doing this was the following, right? The recursive approach was to move n minus 1 of these disks, okay, from pole A to pole B using pole C as the help pole, okay. And then when you are done doing that, you can move this to C, and then you can move the n minus 1 disks that are here to C, okay. So that's the problem, right? So the initial problem, or let me call it the larger problem. Okay, this is a problem of size n, where you have n disks labeled 1, 2, 3 up till n. Okay, the larger problem, yes, the number of poles is fixed, is 3. It's not an input. That is, the number of poles is fixed to be 3. Okay, so the larger problem is to move n disks from pole A to pole C, okay, using B as help. Okay. And now we realize that we can write this larger problem, we can solve this larger problem by solving 2 smaller problems. Okay. In terms of, we can combine the solution of 2 small problems to construct the solution of the larger problem. And these 2 smaller problems are the following. Okay, so smaller problem number 1 is move n minus 1 disks from pole A to pole B using C as a help pole. Okay, and smaller problem number 2 is move n minus 1 disks from pole B to pole C using A as a help pole. Okay, so this is the larger problem that we are trying to solve, and we realize that if we solve these 2 smaller problems, then we can just combine them in a sequence. Okay, solve smaller problem number 1 first, then move the largest pole, the nth pole. Okay, so the last pole from pole A to pole C, and then solve the smaller problem number 2. Right? If you combine them, if you do them in this order, smaller problem number 1, then move the largest disk from pole A to pole C, then solve the smaller problem number 2. Okay, then you solve the problem. Then you have successfully, you're going to be moving all the disks. Okay, without violating the constraint that you had. from pole A to pole C. Okay, so that is the recursive program then, right? And we're going to we're going to look at the recursive program as to how you write the larger problem in terms of the smaller problem. So how do you solve the smaller problem? Well, it's simple. You just make a recursive call to itself. Okay. How do you solve the smaller problem number 2? Well, again, recursive call to itself, right? So that's how you want to approach this particular problem. It's in the base case is something very simple. If the number of disks to be able to move from A to C is just 1, you just move it, right? So there's no problem. You just straight away move from pole A to pole C without any issues. Okay. Okay. So do you guys want to look at the code? We'll just do everything afresh, right? So we're going to write the code from fresh. Do you want the code or your code? We are going to experiment a little bit with the code, try to prove the come to this and try to prove the correctness of the code, and then perhaps do some analysis as to how much time this is going to cost you, how many moves is this going to cost you. Okay, so do you guys want to see the code, or are you comfortable with this? So anyone? Can I skip the code and just straight away go to oh, you want to see the code? Okay. All right. So let me just share this window then. Okay. Okay. So let's write the code afresh. Okay. So I'm going to just do vi hanoi.c. Okay. Then hash include stdio.h. Okay. Let me write the main function first. Main intn. Let's ask the user the input n. Okay. So just printf number of disks. Okay. And then we'll just do a scanf. Okay, and then once we are done, we're just going to make the call to this recursive function. So Hanoi, let's call it Hanoi. And what are we going to pass? Well, the number of disks you want to move, that is n. And we are going to move the labels of the disks, the from disk, the name of the to disk, where we want to move it, and the help disk, right? So we're going to pass, say, A, B, and C. Right? So these are just characters that we can copy. Okay, so let's write our recursive function. So it's not supposed to return anything, right? So let's say it's void Hanoi. We have to print everything, and this is supposed to take the number of disks. So intn, then char from, char to, char. So let's call it help. Okay. All right. So now let me ask you guys. Okay. So what is the base case, right? So when you write these kinds of recursive functions, the first thing you write is the base case, the simplest case, right? Because look, when you make these recursive calls, you're making calls to functions with smaller and smaller values, right? So in this case, you will make recursive calls with value of the first parameter, which is smaller and smaller. Now it's going to typically unfold to one of the base cases. Okay, in this particular case, you're going to make n is going to make a call to n minus 1. N minus 1 is going to make a call to n minus 2, and so on and so forth, right? So it has to unfold to something that is very simple, right? Right. So in the you can write the simplest or the base case in this particular recursive function could be when n is equal to 1, right? So you say that if n equal to 1, then what do you do? What do we do? Yeah, okay. So that so we have something on the chat window. So in this particular case, you just move, right? So you just say that move the disk, okay, from the from pole to the to pole, right? So directly. So there's absolutely no issues over there, right? Okay. So then we're going to do. And what you're moving it from, and you're moving it to, right? So as simple as that. And then once you're done, you can just say return, right? Otherwise, what do you want to do? Well, let's go with our plan, right? So what is the plan? If the number of disks is not one, then there's a complication, right? So then you have to basically move n minus 1 disks from the pole from to the pole help using 2 as the help, right? So then you have to make a recursive call for that, right? So and we okay, so you make n minus 1, then you have to make it from to help using 2, right? Now you that moves n minus 1 disks from the from pole to the help pole, right? The auxiliary pole, okay, using 2 as the help pole. Now once you're done, you only have one thing to move from the from pole to the to pole, right? So we are going to just do that. So printf, okay. So we can just do move disk from %c to %c, okay. And the pole that you're trying to move and the disk that you're trying to move is n, that you're trying to move the nth pole, and you're going to move it from the from thing to the to pole, right? Okay. And once you have done that, what you're going to do is you're going to just make the call to the other function, because you have to move n minus 1 disks. Where are you moving it from? So can somebody complete this call? What am I supposed to write over here?
Help them to.
Okay, so yeah, exactly. Remember, we now have n minus 1 disks in the help pole, right? So we are supposed to, yeah, so we are supposed to move them from the to the to pole, okay, using from, okay, as the help, right? Okay, so and that's it. That's your function, right? So let's see if we made any kind of mistakes here. Okay, it worked out
Sir, I
fine.
think
And yeah, go ahead.
there's %d in the second last call.
Oh, yeah. Just let me check. Okay. Yeah, you're right. Yeah, it should be percent B because n is an integer, right? And I'm also not putting in this. So let's put. So we say C. C. Okay, and let's try. So it's not uniform. It's not looking nice. So let me make it move. Let's make it a little bit nice looking. This is uniform. Okay. Okay, now it looks nice. So let's see. So is this doing it correctly? So what? Okay. So let me copy this. Okay. So I can't share two things at one time. Okay. So let me try to copy this and see whether I can paste it here. Yeah, it does work. Okay, so I can do this. Okay, so let's go back to our where we are trying to write things. Okay. So look, so this is the solution that we got. Let's quickly check whether this actually makes sense or not. Okay, or did we make any mistake, or the solution that we're getting is correct or not? Okay, so here's the scenario. So you have this, you have this, okay, and this, and you have these disk number 1, 2, and 3. Okay. Now what happens? So first thing it says is move disk 1 from A to B. Okay. So it's moving this one from A to B. Okay. So it goes here, right? So this is fine. So I'm going to just do some quick drawing. Okay. So you have this, and this one moves over here. Okay. And then it says move disk from A to C. Okay. So this is disk number 2. So then it says that move disk from A to C. So the largest disk is here, the smallest disk is here, and here we have the disk number 2. So this is 1, this is 3, okay, and this is 2 over here, okay. Now it says move disk number 1 from B to C, okay. So B to C. So then the situation is going to look something like this. So you have disk number 3 over here, this becomes empty, and this contains 2 and contains 1, okay. Now it says move disk 3 from A to B, okay. Uh, oh, the very first call I made. So I from the main function I called Hanoi n comma a b c. Sorry, right? So this is so this says that you're supposed to move the disks from disk A to disk B using C as the help, right? So I was supposed to give A, C, B, right? But then it's fine. It's fine. Suppose that is our goal. We want to move all these disks from A to B using this as the help pole. Then this function actually is correct, right? So we are getting the correct answer. Now you move this from this to this, and then you can move this to this. So it seems to be giving the correct answer. Okay, you can quickly check that this indeed, if you just follow all these moves, then indeed this is the right answer. Now, let's look at the quick analysis, right? So as to why, suppose you have to prove to somebody that, look, this recursive function is indeed going to give you the correct answer, right? So it's going to give you the moves to move all the n disks from the from pole to the to pole. Right? So how would you go about proving this, right? And the proof, as we said in the class, follows simply by a mathematical induction argument, right? So you do mathematical induction to prove this. Okay. And when you do mathematical induction, the very first step is actually to define your propositional function P of n, right? So I mean, essentially what we are going to do is we are going to do induction on this integer n. Okay. And for recursive programs, typically this propositional function is almost given to you. It's ready made, right? It's you don't have to think about what is the right loop invariant as for iterative programs. Here, you roughly know what this propositional function is going to look like, right? So what does this say? Propositional function. Well, here is what we can say, right? So Pn means that the program or the recursive function outputs the correct sequence of moves for n disks. Okay. And what are we intending to prove? What do we want to prove? We want to show that this program is correct for every n, right? So we want to show that for all n, right? So for all positive n, right? Pn. This is what we want to show, right? So this is what we want to show. Your program is going to give you the correct sequence of moves for any input, for any integer n, right? And how do you go about doing that? Well, the template for mathematical induction is almost fixed. First, you do the base case, okay, where you show that P1 holds. Okay, so can we check? Can we quickly check whether P1 holds or not? If if you give input 1, okay, to your program, right? If the number of disks that you want to move is 1, you make a call to Hanoi 1 A C B, right? That's what you want to get. Does your program work correctly? Does your program return the correct sequence of moves to move from pole A to pole C? Yes, that corresponds to the base case. Okay. So that corresponds to the base case because the first thing you do is check whether if the number of disks to move is just 1. If it is just 1, you just move it from the from pole to the to pole. So indeed, it is going to be correct, right? And then you do the inductive case, okay, where let's do strong induction, where you assume P1, P2, okay, Pk for some arbitrary k that is positive, and then you show that that Pk plus 1 holds. All right. So Ashutosh, you shared something, but I'm not able to see that. I don't know why. Can I change some settings to be able to allow you guys to share things? I don't know. Yeah. Okay. So if you can just say in the chat window or just say it aloud, I think that will help because I'm not able to see the image that you shared.
Sir, that is just for help. I mean, that is not a question. It's okay.
Okay. ठीक है. All right. So we want to show that Pk plus 1 holds, given that you've already argued that your program is going to, or your recursive function is going to be correct for disks when you have 1 disk, when you have disk 2 disks, when you're trying to move k disks. For all of them, your recursive function does give you the correct moves. Okay. Now we are trying to show that your recursive function will also be correct for when you are trying to move k plus 1 disk. Okay. So now you just need to do this inductive step, right? So you have k plus 1 disks, okay? So you have k plus 1 disk, k disk number k plus 1 over here, and you have all these other disks, right? So disk number 1, 2, up, right? So that is the problem. And suppose you make a call to your Hanoi function with k plus 1 as the first parameter, right? So what happens? Well, what happens is that your function is going to make a recursive call for moving all these k disks from this pole to this pole using this as the help pole. Okay. Now you can invoke the induction assumption. The induction assumptions when the number is k, right? So what does that mean? That means that your program or your recursive function is going to output a sequence of moves that are correct, okay, in moving these k disks from this pole to this pole, okay. Now, what it entails, what the actual moves are, it doesn't matter. You're just invoking this induction assumption, which says that your program is correct. The sequence of moves that it's going to output is going to not violate the constraint, right? It's going to correctly output the sequence of moves that moves all these disks from 1 to k, from this disk to this disk. Okay? All right. So it's going to give you a valid sequence of moves for moving all these k disks from this to this, and that follows from induction assumption. Now, when all these disks are here, you are moving this from this to this, which is also valid, which is fine. The constraint is not violated. Now, once the largest disk is here, you move all these k disks from this to this, again making a recursive call. And even at this step, you can invoke the induction assumption that the sequence of moves that your program is going to output for moving these k disks from this pole to this pole is going to be valid sequence of moves. It's not going to be invalid. None of those moves are going to be invalid, right? Now, again, it may entail whatever the moves could be very complicated, right? But it's not going to violate because the largest disk is at the bottom, right? So whatever moves are involved in moving these k disks, right? It's not going to be conflicting with this larger disk because this is the largest disk and it's already at the bottom, right? So you can just imagine that your surface starts here, essentially, right? So if that makes your thinking easier. But all you're doing, yeah, exactly, right? So as Adil said that, aren't we assuming that the valid sequence of moves for k does not involve moving the k plus 1 disk at all. The k plus 1 disk is not even there, right? When you're talking about problem of size k. That's what I'm saying, right? You can just imagine, you can just ignore it, right? So right now, these poles are standing on this surface, right? So essentially what I'm saying is that you can just imagine that the surface, these poles are standing on this surface, okay? The largest disk is at the bottom. It's not going to conflict with the movement of these k disks in any manner. Because the largest disk is already at the bottom, you can place any of these k disks on top of it. It's not going to violate the constraint, right? So what you're essentially saying is that as long as all these k disks are moved, okay, without any conflict, without any violation of the constraint, is going to be fine, right? So notice that even without thinking about what those exact sequence of moves are, the mathematical induction argument should convince you that your answer is going to be correct, right? We just use induction, right? So we just invoke this induction assumption that your program returns the correct answer for inputs of size k, right? And that's it. This is a valid mathematical proof, right? And you are convinced that your function is going to return the correct answer for every n, whatever input that you give, it's going to return the correct answer, right? Just using a mathematical induction argument, you can convince yourself that this program returns the correct answer. And now you can actually try experimenting, and Ashutosh, the video that he had sent, now you can just look at those videos to just get more sense of exactly what those moves, what those precise moves are. Or you can just look at the output of the function that we wrote, the printout. You can take a printout and just see, analyze that. But you know that whatever it is, right, that's just for fun, exactly how to move. But you don't need to look at that, right? You don't need to look what those precise moves are. It's just to just for fun, right? So this argument, this mathematical argument, is enough or is sufficient to be convinced that whatever those sequence of moves are, they are going to be correct. None of the constraints are going to be valid. That's what I mean when I say that sometimes it's easier to think in terms of a recursive function, right? It's easier to think recursively, right? Because you can write the solution of a larger problem in terms of a smaller problem, and if you are able to do it correctly, if you are able to do this mathematical induction argument, right, then you are convinced that your function is correct, right? And then you can just look at it. Okay, so these are precise moves, these are the precise things that are happening now, but you don't need to, right? So you can be convinced that your program is correct, your recursive function is correct. Okay, so there's sometimes this is like a classical example where which shows the power of recursive thinking, right? So which really shows the power of thinking recursively. All right. Okay. All right. So now let me ask, since we're talking about towers of Hanoi, let me ask some interesting questions. Okay. So what do you think? What is the number of moves? What is the number of moves when moving n disks? So what do you think? What would be the total number of moves when you're moving n disks? Does anyone have a way of analyzing this, of way of figuring this out? The total number of moves, and single move is moving one disk from one pole to another pole, right? So what could be the total number of these moves that are going to be there in the entire execution of this particular program? Okay, so let's note, let's see whether we can obtain some kind of pattern. So we were trying to move three disks, and the number of moves involved are like 1, 2, 3, 4, 5, 6, 7. Right? Okay, so there's 7. And okay, so 3 disks, 7 moves. Okay, 1 disk, well, 1 move, that's simple. 2 disks, if there are 2 disks, how can you move it? Well, you have 2 disks. That cannot be too complicated, right? You have 2 disks, so you move this from here to here. Okay, so that's 1. Then you move this from here to here. That's 2, and then you move this disk from here to here. So that this is going to be 3, right? So 3 moves. Right. So 4 disks, 5 disks. What do you think? Okay, so let's name it, right? So let's give it a name. Let's define a function, and then we can perhaps try to write the function. Let's say that Tn denotes the number of moves when moving n disks. Okay. So now we have T1 equal to 1, T2 equal to 3, T3 equal to 7, that we have figured out. Okay, so all right. Now what is going to be T4? Can I write T4 in terms of, say, T3? Yeah, so what is the relationship between T4 and T3? Maybe you can give it, right? And if you can write T4 in terms of T3, then we know T3, right? So maybe we can figure out what T4 is going to be. Right, exactly, right? So as Tushar says that, well, T4, can't you just say that it's going to be T3, okay, plus 1 plus T3, right? Right, because what are you trying to do? Well, you move 3 disks from the first pole to the middle pole, Then you move the largest disk, that's one move. And then you again move 3 disks from the middle pole to the end pole, right? So this is going to be 2 times T3, okay, plus 1. So this is going to be 15. Okay. So and then you can just simply say it. So T5 is going to be simple, right? So T5 is going to be 2 times 15 plus 1. So that is 31. And now you start seeing some pattern, right? So 1, 3, 7, 15, 31. Okay. Can you see a pattern in all these numbers? And as Mohit points out, minus 1 because it fits, right? Look at this. It fits for 1. So if you have this formula, then it is correct for 1. So T1 is equal to 2 to the power 1 minus 1. That is 1. T of 2 is 2 to the power 2 minus 1. So that is 3. That is correct. T of 3 is 2 to the power 3 minus 1. That is 7. Okay. So maybe this is the general formula. This is how it looks like. This is the closed form expression for Tn. Okay. Now let me ask you, can we prove that this is indeed the formula? It works out, it checks out for 1, 2, 3, 4, 5. But in general, can you prove it? How would you prove it? So let me just know that mathematical technique that you'll use, because once we just figure out what is the template or what is the way of proving, we'll just move on, not look into the details. What is the mathematical way of proving that this is the number of moves for any n, right? So this is what the closed form expression for n is. How do you prove this? So if you give the input n, then the number of lines that your program is going to print is 2 to the power n minus 1. How do you prove this? Yeah, go ahead. Either type in the chat window or just say it aloud. I guess it's too simple a question to ask. That's why you guys are not responding. So how do you prove this rigorously? That Tn is going to be 2 to the power n minus 1. Induction, right? So yeah. So Aditya, yeah, go ahead.
Yes, so can we use a result that Tn is equal Tn plus 1 is equal to Tn minus 2 times Tn plus 1?
Yeah, exactly, right? So yes, exactly. That's exactly what we're going to do, right? So
For
we are
Tn
going to
plus
first
1
observe.
result for Tn.
Yes, so
Yeah,
Tn
so
minus 1 is 2 to the power Tn minus 1, and then we have the relation that T of n is equal to 2 times T of n minus 1 plus 1. So when we substitute
right.
for 2 to the power n minus 1 inside of T to the power T of n minus 1, we get 2 into 2 to the power n minus 1 plus 1. So that's 2 into 2 to the power n, that's 2 to the power n plus 1 minus 2 plus 1. So it becomes 2 to the power n plus 1 minus 1.
Exactly, right? So exactly. So what you're outlining is what kind of an argument? First of all, the observation that you make is you can write Tn in terms of Tn minus 1, and you guys have already told me, right? So T of n is 2 times T of n minus 1. Okay.
Plus 1.
With the base case, yeah, plus 1, right? So 2 times T of n minus 1 plus 1, right? So with the base case that T of 1 is equal to 1, right?
Yes, sir. Yes, sir.
Yeah, so and that is true for any n greater than or equal to 2, right? Now what you do is just do a mathematical induction. So
So we can write P of T of n in a general form of k as T of n is equal to 2 to the power k T of n minus k plus 2 to the power k minus 1.
right. So matlab you're trying a different name of the variable, but that's fine. All of the idea is basically the same. You prove it by mathematical induction, okay? And in a mathematical induction, what do you do? Well, the first thing you define is your propositional function p of n, right? So where and the propositional function here is very simple. So t of n is 2 to the power n minus 1, right? And then you do the base case, you argue that P of 1 holds. Okay. What does P of 1 say? P of 1 says that T of 1 is 2 to the power 1 minus 1, that is 1, which is correct, right? You just need 1k. And in the inductive step, which is what you guys are trying to suggest, okay, we assume that P1, P2 up till Pk holds, okay, for an arbitrary k that is greater than or equal to 1, so holds. And then you try to show that Pk plus 1 holds, right? So this is what you're trying to show. Let's see. Now, the first thing you observe is that Tk plus 1, by our observation that we made over here, that this holds for any n greater than or equal to 2, right? So Tk plus 1 can be written down as T times 2 T of k plus 1, right? And now you use the induction assumption. The induction assumption says that Pk holds. Now, what does Pk holding mean? Pk holds mean that T of k is equal to 2 to the power k minus 1. That's what Pk means. Pk holding means, right? So then Tk plus 1 is going to be equal to 2 times 2 to the power k minus 1 plus 1. So let's just do simple maths. So this is going to be 2 to the power k plus 1 minus 2 plus 1. So this is going to be 2 to the power k plus 1 minus 1. Okay. And that's it. This implies that Tk plus 1. And that's it. Inductive base case done. Inductive step done. What does that mean? That means that for all n, Pn, okay. And what does that mean? That means that the number of moves, okay, for any n is going to be equal to 2 to the power n minus 1. So that's again, that's why mathematical induction is so central to computer science. It's you can use it in so many different ways, in so many different situations to prove various quantities, right? So that's why we emphasize whenever I teach algorithms or data structures, the very first tool that I try to make the class comfortable with is mathematical induction. Because look, what are you trying to do? You're trying to prove that your program is correct, right? Your program works correctly for inputs of all sizes, any size, right? And that almost fits into the template of mathematical induction. You're trying to prove that your program is correct for input of size 1, input of size 2, input of size 3. So what do? You do mathematical induction. You try to show that your program works correctly for inputs of size 1, that's the base case. And then you argue that if your program is correct for inputs of size 1, 2, 3, 4 up till k, then it's also going to be correct for input of size k plus 1, right? And once you do both these steps, what does principle of mathematical induction says? It says that your program is correct for every input, for inputs of solve, right? So that's why mathematical induction is very central to analyzing algorithms, analyzing correctness of programs, right? So doing proof of correctness, because the proof almost fits into very nicely into the template of mathematical induction. Okay, so just make sure that you're really comfortable with mathematical induction, and a lot of these checking that whether your recursive program is correct or not, you can just do it using mathematical induction. Okay, so this entire thing has taken me a lot of time, and even example that we wanted to discuss, but is somebody trying to say something? Yeah. So I had one more example that I wanted to discuss with you guys, and that was insertion sort. And I wanted to give you some sense of, again, a recursive program for insertion sort. So are you guys fine staying with me until 1?
Yes, sir.
Okay. All right. So let's do that example. So, oh, Kushal says that how did we guess T of n, right? Well, it's actually, yeah, so that's, you used a very correct word. We actually tried to guess, right? So there is some guesswork involved, but it was not a wild guess, right? So we did some basic cases. We said that, okay, so we started looking at patterns. For one disk, it was 1 move. For 2 disks, it was 3 moves. For 3 disks, it was 7 moves. For 4 disks, it was 15 moves. For this, it was 31 moves. So we did make a jump guessing, right? So we guessed this, but it was not a wild guess. We looked at this pattern, and all this suggests that one thing that fits is actually 2 to the power n minus 1, right? So, and that's why somebody suggested 2 to the power n minus 1, because 2 to the power n minus 1 fits into all these cases. But then we should not be convinced, right? Because maybe it's actually the formula is something else. 2 to the power n minus 1 happened to be a lucky guess, right? So maybe for just disks 1 disk, 2 disk, 3 disk, 4 disk, 5 disk, right? Maybe it will not be correct for six disks, right? So just guessing 2 to the power n minus was not sufficient. We went ahead and actually proved it, right? Inductively. Okay. So it's a very valid point that Kushal is raising, that look, you just guessed it, didn't you? Well, yes, we guessed it, but it was based on a particular pattern, but we didn't stop there. We proved it that that is going to be correct. Okay, we gave a mathematical proof that that is the right expression for TN, right? So how do you actually guess it in a general scenario? Well, the more intuition that you develop, you start looking at these patterns, what is the kind of pattern that is being generated, then you make a sort of a guess, and then you don't stop there, you try to prove it by induction that your guess is indeed correct. Okay, so this actually you'll find it funny, this method of getting these bounds on these number of steps or number of moves or the running time, it's actually called the guess and check method. There's something called in the literature, it's called guess and check, right? So you guess the bound and then you actually check using mathematical induction. You prove that your guess is indeed correct. Okay. All right. Yeah, go ahead.
So can we do it in a certain way that the number of steps is greater than that what we found with the formula 2 to the power k plus 1 minus 1? I mean, is that the least number of moves?
Oh, yeah, that's Aditya is raising a very good question, right? So what we have found is this expression t to the power tn is equal to 2 to the power n minus 1. Now what we have found is the number of moves in our recursive program. Right? And I will highlight this, our recursive program, the program that we wrote, that this is a bound for that particular program. But what Aditya is trying to say is, well, it's just the number of moves in our program. Maybe there could be another program, maybe there could be another sequence of moves that doesn't take 2 to the power n minus 1 steps. Okay. Perhaps you can move n disks with lesser than 2 to the power n minus 1 moves. Maybe we didn't write a program that minimizes the number of moves. We just wrote a program, right? So what do you guys think? Can you move n disks with using moves lesser than 2? Is using lesser than 2 to the power n minus 1 disks moves. So what is that? Let me ask you to just guess. Yes, no. It's a yes, no question. Can you move with lesser than 2 to the power n minus 1 move? Yes or no?
So like for 1 and 2 n is equal to 1 and 2, there could not be lesser moves.
1 and 2, yeah, that seems like, yeah, you can, it's a simple case, you can just argue that you cannot make this number. Yes, okay. But what about in general for larger values then?
Sir, please repeat the question.
Okay, so let me just write it down, right? So so remember, so this 2 to the power n minus 1 is the number of moves of our program, recursive program. Okay, so the question that we are asking, so the question that Aditya is asking, is it possible to move n disks using less than 2 to the power n minus 1 moves? This is the question that I'm asking. So what do you guys think?
So given the rules that we have to move only one disk and larger disk should be at the bottom of smaller disk, then I think that we can't move less than 2 to the power n minus 1 moves.
Okay. Can you explain why? Can you tell me why?
Because our program just use these basic rules, and I mean we didn't use any other conditions than these things. Then I think it is the minimum number of moves.
Well, okay. So you're giving me an intuition, but can you convert it into a like a mathematical argument? Because it's not convincing me, right? You're just saying you. So just let me rephrase what you're trying to say. You're trying to say is that well, your program, the program that we wrote, did worked correctly, and that's why it has to be the minimum number of moves. But
So
that's not an argument, right?
So we use the fact that t of n is equal to 2 t of n minus 1 plus 1. That is correct, I think. I mean, and then we can use this formula recursively to generate another formula of t of n, which will be. Can you write it down?
Bolo.
T of n is equal to 2 to the power k
equal to 2 power k. Your voice is breaking. So can you type in the chat window? Maybe we can see the formula there.
Okay, sir. So is it visible?
So what does that mean? What is k?
So k can be any integer from 1 to n minus 1.
No, but what does this try to? What are you trying to capture with this?
So then we
What
will
are you trying to
put the
say?
value of k as n minus 1.
No. Look, Ashutosh, you are trying to just solve that equation, right? T of n equal to 2 times T of n minus 1. This question is slightly different, right? So this is not asked, this is not trying to show that whether you solved it correctly or not, whether T of n equal to 2 of T n minus 1 plus 1, did you do the calculation correctly or not? It's asking something independent of the program. It's asking, this question is asking, is it ever possible? Maybe it might be possible to move the disk in some other completely different manner, right. That has got nothing to do with the program. Completely कोई completely different program आप लिख दीजिए which moves from the first disk to the last disk, right? वो program may be completely different, nothing to do with this program, and that program may take say can move it with less than 2 to the power n minus 1 moves. Okay, yeah, if a program, just leave the program. I'm just asking a mathematical question. Is it ever possible to move n disks using less than 2 to the power n minus 1 moves? Okay, and this question has to do nothing with our recursive program. This is an independent question that Aditya is asking. Okay, because our program makes uses 2 to the power n minus 1 moves. Maybe it might be possible to move using less than that, right? That is the question that. So yeah, so actually this is the best that we could do, right? And there's a way of thinking about it. There's a way of showing this term 2 to the power n minus 1 is actually a lower bound of the number of moves that you'll remove the disks from the first disk to the last disk. And the way to think about it is the following, right? Now we are trying to move all these disks from the first to the last one, right? And you have the largest disk sitting over here. Now, whatever the sequence of moves are, doesn't matter. At some point, you are going to move the largest disk from one pole to some other pole. Doesn't matter, right? You are going to move it from one pole to the other pole. Now, just look at that instant. What is the status? What could be the only possibility when you move the largest disk? Right? Now, the only possibility at that instant when you're trying to move the largest disk is that all the other disks, n-1 disks, are neatly stacked, okay, in decreasing order on one of the poles. That's the only way you can even touch this disk, right? Because if there's any other situation, you cannot move the largest disk. The largest disk can only be moved when one of the pole is empty. The one of the pole which has the largest disk, the largest disk is the only disk because that is the point when you can actually move it. And all the remaining disks are neatly stacked, okay, on one of the poles. At that point of time, you're going to be able to move it. Okay. And now you can again use an inductive argument. Okay. So once the largest disk has been moved, your goal is to move all these k or n-1 disks from one pole to the other. What is the minimum number of moves that you'll require to move these n-1 disks? Okay. So you can ask, you can define another quantity s of n. Say, okay, s of n is the minimum number of moves. Okay, you can define a quantity s of n to be the minimum number of moves. Again, this quantity has got nothing to do with the program. Minimum number of moves to move n disks, right? And what we notice with this argument is that Sn, okay, is going to be equal to 2 times S of n-1 plus 1, right? Because look, what has happened at this instant? You have moved n-1 disks from here to here, okay? And the minimum number of moves required is actually n-1, S of n-1. Then you move this disk from this to this, okay? That is 1. You need that. You have to move the largest disk. And then at that point of time, all these n-1 disks are at some other pole. So you will need another minimum number of moves, S of n-1 moves, to be able to move all these here, right? So again, you get a similar kind of equation. And here, it's something different. Here, we are talking about the minimum number of moves, but the equation that you have is the same, okay? And then you can prove by mathematical induction that the minimum number of moves, again, you get the same equation, the same function as before, 2 to the power n-1. Okay, so Aditya, is this clear? It's a different argument. It's got nothing to do with the program. We are arguing in general.
Clear. So, but one more
Okay.
thing, like after every change, we define the certain orientation, and we make one other constraint that no two orientations should be the same. So, can we find the longest number of moves we can use?
The longest number of moves doesn't even make sense, right? So you can just do useless number of moves, right?
No, so the constraint is no two combinations should be same after a certain move.
No two configurations. Okay. Where you have the configuration, you can define the notion of a configuration. What is the longest number of? Yeah, so that's interesting actually. Yeah, I've not thought about that, because that's not a natural question that people typically think when towers of moving. That's an interesting question.
Because for n is equal to 3, I could find a way to move for something greater than 7 moves.
That's interesting. Actually, I have not given it a thought, right? So if I start thinking it right now, it will not be a very helpful discussion. Okay, so if you want to discuss, just send me.
We can discuss it over Piazza.
If more students are interested, why not? Yeah.
Okay.
Okay, or you can feel free to just drop me an email. Okay, so we'll talk about it. Okay. So it's already 12:39. So let's do insertion sort really quickly then. Okay, so maybe in 20 minutes we can discuss. Okay, so let me just go back here and let me talk about insertion sort. Now, there's a recursive way of looking at this insertion sort, and the recursive way is the following, right? So what is the problem? You're given, the problem is given an array, and let's simplify the discussion, saying that, okay, so given an array containing n distinct integers, okay, sort them, increasing order, right? So this is the problem that we are trying to solve. And let's again think recursively about this problem. Now the larger problem is could be sorting array of size n. Okay, and this can be written down as the following smaller problem. Sort array of size n minus 1, right? Now let's think about it. So we want to sort an array of size n, and we want to be able to do it using a sorted array of size n and then just doing something with it, right? So there are various ways to do this. And in the insert idea that you have is the following. Given array a1 to n, okay, so we typically use this notation to denote your array is of size n, and the indices that we use is 1 through n. Don't worry about the programming. In programming, arrays are typically indexed 1 to n minus 1. We can go back and forth between these small shifts when we write program, but so given, or if you're comfortable with that notation, you can just do this. Okay, given okay, what you're going to do is sort array a0 to n minus 2. Okay, once you have sorted this array, the first n minus 1 elements, we are going to do insert a of n minus 1 within a0 to n minus 2. Okay, and this is written in a sort of a very informal fashion, but the idea is to just convey the high level idea here. So that's why informal notation is going to be fine over here. So what we are trying to do is look, you are given an array, okay, and you want to sort them. So indices 0 through n minus 1. So what you're trying to do is to first forget about the last element, right? So just look at this part of the array, the first n minus 1 elements. And for the smaller problem, you solve the smaller problem, right? So the smaller problem is to sort this array of size n minus 1. Okay, so you sort it, and once you get this sorted array, okay, what you do is look at the last element and find in that sorted array you find the correct location. Suppose it's between, so now you have a sorted array of size n minus 1. You're trying to insert the last element at its correct place. Maybe it's the right place is here. That means suppose this is say 10 and this is 9 and the next element is 11. Okay, so the right place, okay, so and this is 11. The right place for this 10 to be inserted is actually between 9 and 11, right here. So what you're going to do is you are going to shift all these elements by one place, okay, so that you create a gap, and then you are going to put a 10 over here, right? And lo and behold, if you do that, your entire array is sorted because the initial n minus 1 elements are already sorted. You inserted 10 at its right place. So eventually what you're going to get is an array that is array of size n that is sorted entirely. Okay. So that is the recursive way we want to think about insertion sort. Okay. So we can actually go ahead and program. So let me quickly write a program. So you guys are fine. Yeah. Okay. So there are 10 people still here. So I think so. It's fine. Can I take 10 minutes to program?
Yes, sir.
Okay. So just I'm going to shift my window. Let's go back here. Okay. Okay. So yeah, so we are all set. So let me just open a new file. So insertion sort.c. Okay, and we're going to start with okay, and we're going to start writing the main program. So int main, and here we're going to first define an array, right? So int a, and we're going to define the array here itself, right? So why take the input? So let me just define an array of size 10 or 12. Okay, so 1, 34, 12, 99, 24, 15, 87, 87, 55, say 2, okay, 99. So how many elements are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let me add a few more. Say 15, so 17, say 90, and say 20. Okay, and n equal to 13, right? So there are 13 elements. Okay, and we can just say always name the variables descriptive, right? So that is a programming practice that I follow, and it usually helps. So array size. Let me just use array size. Okay, and then we're going to call insertion sort. So insertion sort, and we would just pass the array A and the size of the array n. Okay, so that should be fine. And just to check, let's just print our arrow before and after we call this insertion sort routine. So let's make a function, right? So print array, so a n, and what is this going to? We're going to write this function. Okay, so print array a and array size. Makes chat okay, so that we save time. So for example, I used array size and then I used n over here. Array size. Okay. And we'll have void print array nta ntn. Okay. I or I equal to 0, I less than n plus I print f plus d a of I. Okay, so this is done. Let's write insertion sort routine. So, well, it's going to be void because we're not returning anything. Insertion sort. Okay, so it takes as input int a and int n. Okay. Okay, so we are trying to write a recursive routine. Okay, so tell me, so what is the base case? What should I write? Remember, typically this is the base case for a recursive program, right? What should I write over here? What is the simplest case where you can immediately return?
All elements are sorted.
All the elements are sorted, but then you'll have to check, right? So there could be simpler, right? Remember, so the way we are making a recursive call, we are making recursive call for smaller and smaller size arrays. So always think in terms of this, right? So in terms of it's going to unfold to the base case. We are making recursive calls to smaller and smaller values of n. So when or two elements or there could be just one element. That might be the simplest case, right? So we could just say that if n equal to 1, then just simply return. Nothing to do. It's the array is already sorted, right? So nothing to do. Otherwise, what do you want to do? You're trying to sort an array of size n. Okay. So what was our plan? Our plan was to first sort the array of size n minus 1, the initial part of the array, and then insert the last element, right? So first we have to sort the initial n minus 1 elements. Itself to sort it, right? So what you can do is insertion sort, okay, a, all right, and n minus 1. Now what do we have? Okay, at this point of time, what do we have over here? We have a sorted array, okay, of, or we can just say that we have a 0 dot 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 n minus 1 n minus 2 sorted. Okay, so that is what we have after this step. So what do we plan to do? Well, we plan to do is we plan to insert a n minus 1, okay, in the correct place within the array. Okay, that is what we want to do. So let's make another function. We want to say just, well, okay, a and that is going to make it clear that what we are trying to do is to insert the last element, the n minus 1th element, in the right place, into a sorted array. Okay, so let's write this function again. It's a void function because it doesn't return anything. So void insert, we have int a and int n. Okay, and we are trying to find the right place for it to insert. Which is the right place to insert? Where are we going to insert it? Okay, remember that a0 through a n minus 2 is already sorted. Okay, and we are trying to find where is this element a n minus going to fit, which is the right place for it to fit. Okay, so how do we do that? Well, we just could do a linear scan starting from A0, A1, A2, A3. As long as A0, A1, A2 are smaller, it's fine, right? So we can keep skipping it. When we hit the first time we hit an element which is larger than A of n minus 1, we stop because that is the point, that is the place we want to insert it. Yeah, Satya Pragna, were you trying to say something?
Yes, I was telling that we will break there by running a loop where it will be greater, I think.
So okay, so that's the plan. Let's do it. Let me define a variable I, and let me define a for loop. So for I equal to 0, I less than n, plus I. Okay, and if okay, so what can we write? If a of I is greater than a of n minus 1, we break. This is what we are trying to say, Satya Pragya?
Yes, sir. In that step, we will return the I or I minus 1 to the next function.
Okay, all right. So now what do we want to do? Okay, so now we have found a place where the n minus 1th element should be inserted. Okay, so how do we insert it over there? Well, notice that we have to sort of shift everything to the right one step so that we create a space to be able to put it right over there. Okay, so how do we do that? Well, we can define another variable and we'll just do some kind of shifting, right? So we can define for j equal to I, j less than n, okay, sorry, n minus 1 plus j, okay, and here we can do the following, okay. So so correct me if I make any mistakes. Okay, so I am storing it in 10 and I'm just going to do n minus 1 equal to a j, sorry, j, okay, and I'm going to do a j equal to 10. Okay, so I'm just exchanging. I'm just pulling out the jth element, okay, and replacing it with the n minus 1th element, and I'm storing it in the n minus 1th element, right? And in the next step, I'm going to go do j plus plus, okay, go to the next one, and then again put. So effectively, I want to shift everything, and I'm using the a minus 1th location to be able to shift everything, okay. So okay, so does this look fine?
Sir, AJ should not go to the end of the array, that is AN minus 1. It should just go one step forward.
Yeah, no, yeah, that is fine. Look, the one step forward, but what I'm doing is I'm temporarily storing it in n minus 1, an minus 1. In the next step, okay,
Yes, sir.
I put it in the j plus 1th position. Right, so I'm doing it. I'm just minimizing my effort a little bit. Does that make sense?
Yes, sir.
So yeah, so you could do it in various ways. You can clearly first shift all the elements and then put a n. What I'm doing is I'm doing it in this manner that look, I start with I, right, and I want to place a n minus 1. In the very first step, I'm going to put a n minus 1 over there, but the element that is there at ai, I'm going to put it at a n minus 1. In the next iteration, I'm going to put that element in ai plus 1 and that element in an minus 1, right? So I'm using the a minus 1 location to do this kind of shifting, right? So that is the way I'm doing it.
Right.
You could do it another way. You could first shift and then put an minus 1. It's fine. Either way, it's going to be fine. Okay.
Right, sir, understood, sir.
So, so hopefully we didn't make any mistakes with respect to any of these things. So let's just go ahead and run this program and hope for the best. Okay. So, and if not, we'll come back and do some. It does work. Oh no, it done. It didn't. Something went wrong. 2, 12, 15, 17, 20, 55, 90, 99. So what happened now? Why is because I had 99 twice in my hand. Oh, so yeah, so it's fine. Luckily, I got it correct in the very first go. So let me change the array and let me just make it 98 or something, right? So because I said all the elements in the array are distinct, right? So that's why I'm just Okay, now it looks fine. Okay, and if you guys want, I can spend like 5 minutes to just do a dry run with a simpler example with just 5 elements. What exactly happened with 5 elements, right? Do you guys want to see that, or if it is fairly clear, then we can just skip that. You can prove correctness again using mathematical induction. Okay, what you will do is base case, inductive case, where the propositional function that you define as Pn just says that the function is correctly sorts inputs of or arrays of size n. Okay, and then in the base case you're going to say that, well, P1 whole 1 because your function is going to straight away return. Okay, and then the inductive step, you just assume that P1, P2 up till Pk holds, because which says that your program is correct, your recursive function is correct for arrays of size 1, arrays of size 2, arrays of size 3, up till arrays of size k. Then what happens at array when you give an input an array of size k plus 1? Well, the first thing you are going to do is to make a recursive call to itself with array of size k. Right, the first you sort the array of size k, right? So the first k elements. Since by induction assumption you have that your program is going to correctly sort the first k elements, and then since you're inserting it in the right place, the last element is the right place, the resulting array is going to be sorted, right? So that is going to be effectively your proof. Okay, and you can go back and analyze the sort of what is the number of times or the if you look at the call tree, the recursive call tree, how many boxes are going to be in the recursive call tree, and so on and so forth. Eventually using that, you can even analyze something called the running time of your program, which I'm going to talk about in tomorrow's class, which is basically the total number of operations that you do. If you count the total number of operations across the entire duration of the program, what does it look like as a function of the input size, which in this case is the number of elements in the array, which is n, right? Okay, so if you want to, do you want to see the a dry run of this program on a simple input? A yes/no answer would do. If you're fairly comfortable, we don't need to look at it, and we can just end this session.
It's comfortable. We got
it's fine. Aditya, I didn't. Okay, so you want to see or you don't want to see?
So it's okay.
Like it's clear.
Oh, it's clear. Okay, yeah, that's what I thought, right? So it's going to be, you can just take this program, just use an input of size 5, an array of size 5 or 4, and see what the recursive calls are made and exactly how that is getting sorted. Okay. Okay, so if that is the case, then let me close this session unless there is some question that you guys have, and you can ask this. Otherwise, I'll close this session. All right, so I don't see any questions. Okay, so let me formally close the session. Thanks everyone for being here. I'll see you in tomorrow's class.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thanks, sir.